It's my honor to introduce someone who's well known to everyone here. He has been an advisor to our industry and certainly a major researcher for reinforcement throughout the concrete industry. Dr. Mayor Tadros is currently the managing member at E-Construction USA. It's located in the greater Omaha area. He's a professor emeritus at the University of Nebraska since 2011, and I'm sure we'll enjoy his presentation.
Thank you very much. It's an honor and pleasure to be here with you today. Thank you for inviting me. I'd like to start the presentation. I assume we can expect questions as I go. So if you see something that you would like to comment on or ask a question about, please do so as we move forward. Some of the materials in this presentation is materials that you've seen before, and maybe some of you have generated yourselves. So we'll start with an overview, and then we go into some other discussions. So the presentation starts with introduction of welded wire reinforcement. I feel kind of embarrassed to introduce it to you, but it's one of the things that I introduce when I talk about it to audience who is not obviously as familiar. Properties and features, fatigue discussion, applications, and then I'll end it with opportunities and challenges. We all know that welded wire reinforcement is made of wire, and the wire is high strength called drawn wire. It's welded in a rectangular grid. We have not found a way to do radial grids and some fancy stuff, but a rectangular grid is just good enough, and that's very versatile at what has been used. It uses continuous electrical resistance welding. That's very important. It's not hand welding. It's not something that you get a certified welder to do. It's all automated with computers. Positioning and welding that are computer controlled. Pressure and heat fusion is what causes the wires to be welded together. So it's highly controlled, very high quality. There is smooth wire and there's deformed wire. Smooth wire is labeled W, deformed wire is labeled D, and if it's a metric units, then it carries the MW and MD designation. Some of you produce wire as large as the equivalent of a number 6 bar, 3/4 inch, which is a W or D45. Some don't produce that large of a wire. I think the majority of you produce wires that are in the 25 range, D25, W25, that can be obtained anywhere in the country and in Canada. Wires as smaller as W1.4 are also produced. And we all know, if I can go back here, we know what that designation means. If it's a 1.4, the cross-sectional area is 1.4 over 100 of square inches. If it's 45, then the area is 0.45 square inches. Very convenient. I can tell you that 80–90% of the engineers in this country don't know what that means. It's very unfortunate. But again, I said it probably 15 years ago when I was invited last time, that this is a great material, beautiful material, but it's one of the best kept secrets in this country or in North America. And that kind of needs to be changed. And I'm seeing that Todd is doing a good job with his group going to universities and to state DOTs. More of that needs to be done. The wire comes in mesh. If you're using it in structural products, not in rolls, and the sheet can be, I meant sheets, it's mesh, but it's sheet that is in 14 foot by 45 foot maximum size. 14 foot may be a bit too much for some producers. 10 foot, 8 foot, 5 foot are common widths. And then the lens can be any size convenient for shipping. Yield strength is up to 80,000 psi. However, there has been strong talk about going to 85, 90, or even 100,000 psi. This is talk that should be encouraged, and there will be part of the discussion on it. Spacing as small as 2 inch has been made. Some companies prefer 3, some companies prefer 4, but you can get a spacing as narrow as 2 inch to be used. If I am misspeaking, somebody needs to correct me, please. Okay, so this is interactive, as I said. You're probably tired of this picture. You've seen it so many times. The carbon content is relatively low. That's why it is such a great material, because it's nice for weldability. It's controlled. And then when you put deformation, unfortunately, it's not standardized. There are negative deformation and positive deformation. But in all cases, these deformations work well in creating this is only smooth one, in creating the bond that's needed between the wire and the concrete. That's one means of creating that bond. The other means is obviously the cross wires that get welded to it. So cold working of hot rolled bars or rods, as you can see in the steps here, you can see that as you draw a rod into wire, and the more you draw it, the smaller the wire gets, and the higher the strength gets, and the lower the ductility, or the lower the ultimate elongation. So that's part of the trade. You get higher strength and lower elongation. And there was talk at the technical committee yesterday, and I have it here. I'm glad that there was that discussion. It helped me out. But I think what I'm saying here is still valid. 1046 is the standard to use. ASTM A82, 185, 496, and 497 are becoming historical standards. Doesn't mean that they're obsolete, but they should be used for historical purposes, such as evaluation of an existing structure that was designed according to these standards. So they will not go away. But people like myself, who makes a living designing structures, should know that when they specify the material, they should specify ASTM A1064. So that is an educational aspect that needs to be passed on. This is the wire welding machine. This is a picture that I've used for years and years. It shows the versatility of the welding machine, changes in spacings, having a cut off in the corner, having different spacing in the horizontal from the vertical, and even within each direction. This bender, sheet bender, is one thing that I work with precasters more than cast and place contractors. Precasters need to know that this bending machine is not an impediment, is not something that they should hold back because they don't have it. I was in Florida a month ago. They were building a bridge, and the precaster there, Durastress, had made a machine that's hydraulic, automated, and it bent a very heavy sheet in practically no time. It was really neat to have the group there that were there watching see how this could be done. It's not expensive. It's something that you should aid or help or promote. The fact that it's a machine that's available, whether you do the bending by hand or you do it in an automated way, it should not be a deterrent. It shouldn't be a difficult thing to do. This is your standard stress strain diagram, and I apologize for getting a bit too technical in some of my talk. The The one thing that you will get from this slide is that on the horizontal axis, strain, which is change in length per unit length. As you stretch the wire, it changes the length. That change in length per the original length gives you a strain. And you compare that with the load that you're stretching the wire to, divide that load by the cross-sectional area to get the unit stress in thousands of pounds per square inch, KSI, kips per square inch. So this could be a typical diagram. In fact, we got this from some of the suppliers as we were doing the fatigue testing about 10 years ago. And the standard then, I believe it's changing, is to use 0.0035 or 0.35% strain go up to get the yield strength that people specify. I think that is probably not the best way to do things. And the 0.2% proof, which means that you go parallel to this line, a distance equal to 0.2, not 0.35. You go parallel to it until you catch the diagram, and that's the 0.2% proof. The 0.2% proof is more of an international standard that just about every else in the world is using. It's going to be setting you up for the future as you go to higher strength steels. It's going to be a benefit. I heard yesterday afternoon that there is a discussion of keeping not a 0.35, a 0.5 strain, which was one of the things that was in the standard that caused me myself to be confused, because there were these two limits, 0.35% and 0.5%. But in the future, I understand you're promoting 0.5% straight up or 0.2% proof or parallel to the slope line. That's great. That's a good progress. That's improvement. I personally would prefer that you stick with one definition, and that's the European definition, and that's what people are using. But I'm sure you have your reasons. So as far as specifications are concerned, there are a number of tests that are being used to validate the product or to accept the product as it is specified by the designer. Some of them are the RAP test. And this one here is one of my absolute favorite pictures. If you can find somebody that will wrap a reinforcing bar in a tight spiral like this with a uniform diameter with no gap between the turns, I'd like to see it. This tells me that the wire product is a very high quality, ductile product. It's bendable, it's malleable. That's an advantage that people should try to promote as much as possible. We also talked about welding. It's not the tack welding, it's not the welder's welding, it's machine welding, it's electric fusion. You don't add new material. The two wires fuse together. There's no welding rod here. It's all fused together under heat and pressure. So again, it's very high quality, but also it could be a bad quality. Again, you have to be careful. And when you send your product, you want to make sure that the welding is done on clean surfaces and it's done properly. Because I've seen sheets that got separated at the welds, even without testing. Of course, the shear test, and I'm just asking a question. The shear test has been around for a long, long time. I think it started with the wire that's used for pipe, 65 KSI, 70 KSI, and then 70 divided by 2, 35. But now we're going to high strength. Don't we want to take the initiative ourselves and tell ASTM that we would like to have this limit raised to a more appropriate limit for high-strength steel. It's just a question I have in my mind because I've seen this for a while and I haven't seen it change.